Welcome to Ring Signatures. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving into a fascinating Python implementation of ring signatures, which is a cryptographic primitive that provides signer anonymity. This implementation demonstrates how one member of a group can sign a message on behalf of the group without revealing which specific member actually created the signature. Think of it like a petition where any board member can sign on behalf of the board, but observers cannot determine which board member actually signed it. Ring signatures are particularly important in privacy-focused applications like cryptocurrency transactions, anonymous voting systems, and whistleblowing platforms. The name ring signature comes from the circular structure of the verification process, where the signature verification forms a closed loop through all possible signers. This educational implementation uses a Schnorr-style approach over an integer group modulo a large prime, which makes the mathematical concepts easier to understand compared to elliptic curve implementations. The code we'll be examining implements the complete lifecycle of a ring signature system. Key generation for multiple ring members. The signing process, where one member creates a signature that could have come from any member. And the verification process that confirms someone in the ring signed, but doesn't reveal who. Throughout this presentation, we'll break down every function, every parameter, and every mathematical operation to build a complete understanding of how ring signatures work at the implementation level. Python shebang and encoding. The first 3 lines of our Python program are standard header declarations that help the operating system and the Python interpreter understand how to execute this file. These lines might seem trivial, but they serve important purposes for cross-platform compatibility and proper text handling. The shebang line, which starts with the #bang sequence, tells Unix-like operating systems which interpreter should be used to execute this script. The specific path used here is a portable approach that uses the env command to locate Python 3 in the system's path environment variable, rather than hard-coding a specific location like /user/bin/python3. This makes the script more portable across different systems where Python might be installed in different locations. The encoding declaration on the second line specifies that this Python source file uses UTF-8 character encoding. This is crucial for properly handling international characters, mathematical symbols, and any non-ASCII text that might appear in comments or string literals. While UTF-8 is the default encoding in Python 3, explicitly declaring it ensures consistency and prevents encoding-related errors on systems with different default encodings. The encoding declaration must appear on one of the first 2 lines of the file to be recognized by Python. These header lines establish the foundation for our program's execution environment, ensuring that the script can run correctly across different platforms and handle the mathematical notation and cryptographic terminology we will encounter throughout the implementation. Educational purpose and security warnings. The extensive comment block at the beginning of our program serves a critical educational purpose while also providing essential security warnings. These remarks establish the scope and limitations of this implementation, making it clear that this is designed as a learning tool rather than production-ready cryptographic software. Ring signatures allow any member of a defined set of participants to sign a message anonymously. The verifier can confirm that someone within the group created the signature, but cannot determine which specific member was the actual signer. This property is called signer anonymity or signer ambiguity. It is fundamentally different from group signatures where there is a group manager who can reveal the signer's identity, or from multi-signatures where all members must participate. The security warnings in these comments are absolutely critical. This implementation uses fixed demonstration parameters that are not cryptographically strong enough for real-world use. The operations are not implemented in constant time, which means they could leak information through timing side channels where an attacker measures how long operations take to infer secret information. There are no defenses against cache timing attacks, power analysis, or other side-channel attacks that real cryptographic implementations must protect against. The comments also mention that production systems would use well-reviewed elliptic curves like ED 25519, which offer better performance and stronger security guarantees than the integer arithmetic approach used here. Real-world ring signature schemes like LSAG, which stands for Linkable Spontaneous Anonymous Group Signatures, or CLSAG, the concise linkable spontaneous anonymous group signature, provide additional features and security properties. It is also worth noting that LSAG 2, which is mentioned in the comments, is actually a multi-signature scheme rather than a ring signature scheme, so it serves a different purpose despite both involving multiple parties. Import statements and dependencies. The program imports 3 essential modules from Python's standard library. Each serves a specific purpose in our ring signature implementation. Understanding these imports helps us appreciate the minimal dependencies required for this cryptographic implementation. The hashlab module provides access to secure hash functions, and we will specifically be using SHA-256 throughout this implementation. SHA-256 is a cryptographic hash function that takes arbitrary length input and produces a fixed 256-bit output. In our ring signature scheme, we use SHA-256 as a hash-to-integer function, effectively treating it as a random oracle in the cryptographic sense. The random oracle model is a theoretical construct where the hash function is assumed to produce truly random outputs for different inputs, which simplifies security proofs even though real hash functions are deterministic. The secrets module is Python's cryptographically strong random number generator, introduced in Python 3.6 specifically for security-sensitive applications. Unlike the older random module, which uses a Mersenne twister algorithm suitable for simulations but not for cryptography, the secrets module draws randomness from the operating system's entropy source. On Linux systems, this typically means /dev/urandom, while on Windows it uses crypt_gen_random. This is crucial because the security of our ring signatures depends on the unpredictability of random numbers used during signing. The typing module provides support for type hints, which are annotations that indicate what types of values functions expect in return. The list and tuple types imported here allow us to specify that certain parameters should be lists of integers or tuples containing specific types. Type hints don't affect runtime behavior in standard Python, but they make the code more self-documenting and enable static type checkers like mypy to catch potential type-related bugs before the code runs. This is particularly valuable in cryptographic code where type confusion could lead to security vulnerabilities. Cryptographic group parameters. The 3 constants defined here, P, Q, and G, establish the mathematical group in which all our cryptographic operations will take place. These parameters define what is called a Schnorr group, which is a carefully chosen mathematical structure that makes discrete logarithm problems hard to solve. The prime number P, shown here in hexadecimal notation, is a very large prime number that defines our finite field. A finite field is a mathematical system where we can perform addition, subtraction, multiplication, and division with a finite set of numbers. All arithmetic operations in our ring signature will be performed modulo P, meaning we take the remainder after dividing by P. This large prime is 512 bits in size, which you can determine by the length of the hexadecimal string. Each hexadecimal digit represents 4 bits, and we have 128 hexadecimal digits here, giving us 512 bits total. The prime number Q is a divisor of P-1, and it defines the order of a subgroup within our field. The order of a group is the number of elements in that group. This Q parameter is much smaller than P, being only 160 bits long, which makes arithmetic operations involving Q faster. The relationship where Q divides P-1 ensures that there exists a subgroup of order Q within the multiplicative group of integers modulo P. This structure is essential for the security of Schnorr-based signatures. The generator G is an element that generates this subgroup of order Q. When we raise G to different powers modulo P, we cycle through exactly q distinct values before returning to 1. The discrete logarithm problem, which asks to find x given g to the power x, is believed to be computationally hard in this setting, forming the foundation of security for our ring signature scheme. In a production system, these parameters would be much larger, typically with p being 2048 or 3072 bits and q being 224 or 256 bits, but these smaller values suffice for educational demonstration. The comment emphasizes that these are hard-coded demo values, unsuitable for real cryptography. In practice, these parameters would be generated using standardized algorithms that ensure they have the proper mathematical properties and security characteristics. Alternatively, they would come from well-vetted parameter sets published by cryptographic standards bodies. Hash to integer function. The h2int function is a critical utility that converts arbitrary data into integers suitable for our cryptographic operations. This function implements what cryptographers call a hash-to-scalar operation, turning diverse input types into uniform integer values modulo q. The function accepts a variable number of arguments through the asterisk pieces parameter, which, in Python, allows you to pass any number of positional arguments that are collected into a tuple. This flexibility is important because we will need to hash different combinations of data during signing and verification, sometimes hashing just a message, sometimes a message combined with public keys, and sometimes multiple values together. The mod parameter has a default value of q, which is the order of our subgroup. This means that by default, the function returns integers in the range 0 to q-1, which is exactly what we need for scalar values in our signature scheme. However, the parameter can be overridden if we need to hash to a different modulus for some reason. Inside the function, we create a new SHA-256 hash object. The loop then processes each piece of input data based on its type. For integer inputs, we convert them to bytes using a fixed-length big-endian representation. The byte length calculation, which divides p's bit length by 8 and rounds up, ensures we use enough bytes to represent any value in our field. Big-endian means the most significant byte comes first, which is a standard convention for cryptographic protocols. String inputs are encoded to bytes using UTF-8 encoding, which is the standard character encoding for text. Any other input type is assumed to be bytes-like already and is converted using the bytes constructor. After all pieces have been hashed together, we extract the digest. This digest is the final 32-byte output from SHA-256. We then convert it to an integer, treating it as a big-endian number, and take the result modulo or chosen modulus. This gives us a deterministic yet unpredictable integer from arbitrary inputs. Modular exponentiation helper. The Modexp function provides modular exponentiation, which is the operation of computing a to the power e, then taking the remainder when divided by m. This operation appears constantly in discrete logarithm-based cryptography because our security relies on the hardness of computing discrete logarithms. Modular exponentiation might seem simple if we were to simply compute the power and then take the modulo, but that approach would be catastrophically inefficient for the large numbers we are using. Consider that g to the power of a 160-bit number would produce a result with thousands or millions of digits before we take the modulo. Such a computation would be impossibly slow and consume enormous amounts of memory. Python's built-in power function, when called with 3 arguments, implements a highly optimized modular exponentiation algorithm. It uses a technique called binary exponentiation, also known as exponentiation by squaring, combined with modular reduction at each step. This algorithm has logarithmic complexity in the size of the exponent, making it practical even for our large cryptographic numbers. The binary exponentiation algorithm works by representing the exponent in binary, and it uses the mathematical principle that a raised to the power of x plus y equals a raised to the power of x multiplied by a raised to the power of y. By repeatedly squaring intermediate results and combining them based on the binary representation of the exponent, we can compute large powers efficiently. Python's implementation is not only algorithmically efficient but also highly optimized in C code, making it very fast. Wrapping this in our own modexp function might seem redundant, but it serves documentation purposes, making it clear what operation we are performing, and provides a single point where we could add timing attack protections or switch to a constant time implementation if needed. Random scalar generation. The rand_scalar function generates cryptographically secure random numbers in the range 1 to q-1. These random values will serve as private keys and nonces in our signature scheme, so their unpredictability is absolutely essential for security. The function uses a simple loop that continues generating random values until we get one that isn't 0. We initialize r to 0, then use secrets.randBelow with q as the argument. The randBelow function returns a cryptographically secure random integer in the range from 0 up to, but not including, q. This means the possible values are 0 through q-1, which is exactly the range of valid scalars in our group. The reason we reject 0 is subtle but important. In our cryptographic scheme, a private key of 0 would result in a public key of g to the power 0 equals 1, which would be a trivial case that could leak information. Similarly, using 0 as a nonce in signing could allow private key recovery. While the probability of randomly generating 0 is vanishingly small for a 160-bit queue, proper defensive programming requires us to handle this edge case explicitly. The loop structure ensures that if we somehow get 0, which has probability 1 in 2 to the power 160, we simply generate another random number. In practice, this loop will almost always execute exactly once, but we're being cryptographically paranoid here, ensuring we never return 0 under any circumstances. Using secrets.randBelow is crucial for security. This function draws from the operating system's cryptographically secure random number generator, which gathers entropy from various sources like hardware interrupts, system timing, and specialized CPU instructions. This makes the output unpredictable even to an attacker who might know the program's state, which is essential for cryptographic applications where predictable randomness would completely break security. Key generation function. The Keygen function implements the fundamental operation of generating a cryptographic key pair for discrete logarithm-based systems. This creates a private key and its corresponding public key, establishing the identity of a participant in our ring signature scheme. The function takes no parameters and returns a tuple containing two integers, the private key x and the public key p, using capital P for the public key as a convention in cryptographic literature. This helps distinguish public values, which are often written with capital letters, from private values, which are written with lowercase letters. The private key generation is straightforward. We call our rand_scalar function to get a random integer between 1 and q-1. This private key must be kept absolutely secret, as anyone who knows X can compute the corresponding public key and create signatures. The security of the entire system relies on the difficulty of computing X given only P, which is the discrete logarithm problem. The public key is computed as P equals G to the power X modulo P. This is a one-way function in the computational sense. Given X, computing P is easy using our modexp function. However, given P and G, finding X is believed to be computationally infeasible with current algorithms and computing power. The best-known algorithms for discrete logarithm in carefully chosen groups like ours have subexponential complexity, meaning they are not as slow as brute force but still impractical for large enough parameters. The relationship between X and P is fundamental to our scheme. During signing, the signer will use their private key X to create responses that satisfy certain equations. During verification, anyone can check these equations using only the public key P. The discrete logarithm hardness ensures that only someone who knows X can create valid signatures for P, while anyone can verify signatures using the public P. Ring signature function overview. The ring_sign function is the heart of our implementation, where we actually create a ring signature. This function demonstrates the elegant hash chain construction that allows any ring member to create a signature that could have been produced by any other member. The function takes 4 parameters that define the signature context. The message is the actual data being signed, provided as bytes. The pubkeys parameter is a list of integers representing the public keys of all ring members, defining who could have possibly signed. The secret index identifies which position in the pubkeys list corresponds to the actual signer, and secret X is that signer's private key. These last 2 parameters are known only to the signer and are what allow them to complete the ring. The return type is a tuple containing E0, the initial challenge value, and S_list, a list of response values. Together, these components form the ring signature. The signature is relatively compact, consisting of one hash-sized integer plus n scalars where n is the ring size. This signature proves that someone in the ring signed without revealing which member. The high-level idea describes the circular hash chain construction. We build a chain of challenges where each challenge is derived by hashing the previous response. For all non-signer positions, we choose random responses and simulate that members challenge. When we reach the real signer's position, we use knowledge of the private key to compute a response that closes the ring, making the chain circular. This construction is beautiful in its simplicity. The simulator positions are indistinguishable from the real signer's position because we are choosing random values in both cases, just at different points in the computation. The verifier can check that the chain closes but cannot determine which position was computed using real knowledge of a private key versus which positions were simulated using random choices. This indistinguishability is what provides the anonymity property of ring signatures. Ring signature. Initial commitment. The signing process begins with the real signer creating an initial commitment. This is a crucial step that establishes the starting point for our circular hash chain. The signer generates a random value U, which serves as a nonce or blinding factor, and uses it to create a commitment value RS. We generate the random value U using our rand_scalar function. This ensures it is a cryptographically secure random integer between 1 and q-1. This randomness is absolutely essential for security. If an attacker could predict or learn the value of U, they could potentially compute the signer's private key from the signature. This is similar to the nonce reuse vulnerability that has broken real-world cryptographic systems in the past. The commitment R_s is computed as g to the power U modulo p. This commitment is hiding, meaning it reveals nothing about U to an observer, yet it binds the signer to this particular random value. The discrete logarithm problem ensures that computing U from R_s is infeasible. This commitment will be used to seed the hash chain that walks through all the other ring members. We then initialize 2 arrays, E for challenges and S for responses. Each array has n elements, 1 for each ring member. These arrays will be filled in as we construct the hash chain. The challenge values are what link consecutive positions in the chain, while the response values are what get included in the final signature. The next step seeds the hash chain by computing E at position secret_index plus 1 modulo n. This calculation produces the challenge for the position immediately after the real signer, in circular order. This challenge is computed by hashing the message together with our commitment, R_s. This hash serves as a random oracle, producing a challenge that appears random but is deterministically derived from the message and commitment. This is where the ring signature chain begins its circular journey. Simulating other ring members. After establishing the initial commitment and challenge, the signing process enters a loop that simulates the signature contributions of all non-signer ring members. This simulation is what creates the anonymity property of ring signatures, as simulated positions are indistinguishable from the real signer's position. The loop begins at the position immediately after the real signer and continues around the ring until it returns to the signer's position. The index arithmetic uses modulo n to wrap around, creating the circular structure. For example, if the signer is at position 2 in a ring of 5 members, we process positions 3, 4, 0, 1 in that order before returning to position 2. For each non-signer position I, we first choose a random response value s at index I. The code uses secrets.rand below with q as the argument, which can return values from 0 to q-1. While the comment notes that 0 is technically allowed for simulated members, in practice we could reject 0 here too for consistency, though it is not strictly necessary for security in the simulated positions. After choosing the random response, we compute z, which represents what the verification equation would produce for this position. The core verification equation is the formula z equals g to the power of s sub I, multiplied by p sub I to the power of e sub I, all modulo p. This equation links the response s sub I to the challenge e sub I, using the public key p sub I. In a real signer's case, this equation will be satisfied because of knowledge of the private key. But here, we are working backwards, choosing s randomly, and computing what z would be. The next challenge, e, at position I plus 1, is then computed by hashing the message together with z. This creates the hash chain that links consecutive positions. Each challenge depends on the previous position's response through the z value, creating a dependency chain that must close properly for the signature to verify. This hash chaining is what binds all the ring members together into a cohesive signature structure. Closing the ring. The most critical part of the ring signature construction is closing the ring at the real signer's position. This is where we use actual knowledge of the private key to complete the circular hash chain in a way that makes the signature verifiable. By the time the simulation loop completes, we have filled in challenge and response values for all positions except the real signer. The loop has walked around the ring and computed challenges based on random responses for everyone else. The final iteration of the loop computed the challenge e at the real signer's position, which we extract and store in the variable e_s. Now, here's the crucial insight. We need to choose a response, s, at the secret underscore index such that when a verifier checks the equation at this position, it produces a z value that hashes to e0, the challenge for position 0. This effectively closes the ring. The verification equation at the signer's position is z equals g to the power of s at the secret underscore index, times p at the secret underscore index to the power of e_s, modulo p. Since we know the private key x_s, where p at the secret index equals g to the power of x_s, we can solve for what s at the secret index needs to be. We need g to the power of s times g to the power of x_s times e_s to equal g to the power of u, where u is our original random commitment. This simplifies to s plus x_s times e_s equals u modulo q, which we then solve as s equals u minus x_s times e_s modulo q. This calculation uses modular arithmetic throughout to ensure the result stays within the valid scalar range. The multiplication x_s times e_s is performed modulo q first, then we compute u minus that product, and finally take the result modulo q again. Python's modulo operator handles negative results correctly by always returning a positive remainder, which is exactly what we need here. The ability to compute this response without revealing x_s is what makes the real signer's position indistinguishable from the simulated positions during verification. Ring signature return value. After completing the ring construction by computing the response for the real signer's position, we have all the components needed for our ring signature. The signature consists of two parts that together prove someone in the ring signed the message without revealing who. The first component is E0, the challenge value at position 0. This single integer serves as the entry point for verification. A verifier will start with this challenge and walk through the ring, computing successive challenges by following the hash chain. If the signature is valid, this chain will eventually loop back to produce E0 again, hence the circular or ring structure. The second component is the list S, containing the response values for all n-ring members. Each response is an integer modulo q, and there is one response for each public key in the ring. These responses are what the verifier will use in the verification equations, together with the public keys, to compute the intermediate z values that drive the hash chain forward. The signature is returned as a tuple containing E0 and S. This signature is relatively compact, one hash-sized value plus n scalar values. For our 160-bit queue, each scalar is 20 bytes, so a signature for a ring of 5 members would be about 20 plus 5 times 20, equaling 120 bytes. This is larger than an individual signature would be, but still quite practical for most applications. Importantly, this signature reveals nothing about which ring member actually signed. The value E0 is a hash output that appears random. The response values S are all either random values we chose for simulation, or a value computed from our private key that is indistinguishable from random. An observer cannot determine which response corresponds to the real signer versus the simulated ones, providing perfect signer ambiguity in the information theoretic sense, assuming the hash function behaves as a random oracle. Verification function overview. The ring_verify function implements the verification procedure that allows anyone to check whether a ring signature is valid, without learning who actually signed. This function only uses public information: the message, the public keys of all ring members, and the signature itself. The function takes 3 parameters. The message parameter is the bytes that were allegedly signed. The pubkeys parameter is the list of public keys defining the ring, which must be the exact same list in the exact same order as was used during signing. The signature parameter is the tuple containing E0 and the list of responses S that was produced by the ring_sign function. The function returns a Boolean. It returns true if the signature is valid, meaning someone in this ring signed this message. Otherwise, it returns false. This could indicate tampering with the message or signature, using the wrong public key list, or an incorrectly constructed signature. The verification process is quite simple. We rebuild the hash chain from scratch, using only public information. This starts with the initial challenge E0, then walks through each ring member's position. For each position, we use the response from the signature and the public key to compute a z value. We then hash this to get the next challenge. If the signature was properly constructed, this process will eventually produce a challenge that equals the initial E0, which proves the ring closed properly. The first step in verification is unpacking the signature tuple into E0 and S, then checking that the length of S matches the length of pubkeys. This length check is a simple sanity check to ensure the signature was created for a ring of the same size. After this basic validation, we are ready to walk through the ring and verify that the mathematical structure is correct. Verification loop process. The core of verification is a simple loop that reconstructs the hash chain using only the public information available in the signature and public key list. This loop demonstrates why ring signatures provide verifiability without sacrificing anonymity. We initialize the variable E with E0, the initial challenge from the signature. This challenge serves as our starting point. In a valid signature, this challenge was either the hash of the real signer's commitment for position 0, or it was the challenge that resulted from the simulation of the last ring member, depending on where the real signer was positioned in the ring. The loop iterates through each position I from 0 to n-1, processing every ring member in order. For each position, we reconstruct exactly what the signer computed during the hash chain construction, but now we are doing it using only public information. We do not know which positions were simulated and which were real, but that does not matter because the same verification equation works for all positions. For each position I, we compute z using the verification equation. Z equals g to the power of s at index I, multiplied by p at index I to the power of e, modulo p. This equation combines the response value from the signature with the public key and the current challenge. If this position was simulated during signing, z equals the value that was computed when choosing the random response. If this position was the real signer, z equals g to the power of u, where u was the original random nonce, because the signer chose their response to make this equation work out. After computing z for position I, we immediately use it to compute the next challenge by calling h underscore to underscore int with the message nz. This produces e for the next iteration of the loop. Each challenge depends on the previous position through this hash chain mechanism. After processing all in positions, the variable e contains what should be the challenge for position 0 again if we've completed a valid ring. Verification success condition. The final verification step checks whether our reconstructed hash chain closed properly by comparing the final challenge value with the initial challenge E0. This single comparison determines whether the signature is valid or invalid. After processing all in-ring members in the verification loop, the variable e contains the challenge. This challenge resulted from hashing the message with the z value, which was computed for the last ring member at position n-1. If the signature was constructed correctly, this final challenge should equal E0, the initial challenge we started with. This equality means the hash chain formed a complete circle, returning to its starting point after walking through all ring members. The return statement simply checks equality. Return E equal operator E0. If this comparison evaluates to true, the signature is valid, confirming that someone in the ring signed this message. If the comparison evaluates to false, the signature is invalid. This could have several causes. The message was modified after signing, the signature was tampered with, the wrong public key list was used, or the signature was never validly constructed in the first place. The beauty of this verification is that it reveals nothing about which ring member actually signed. Every position in the ring was processed identically using the same verification equation. We reconstructed z values for each position and chained them together through hashing, but there's no way to distinguish which position corresponds to the real signer versus the simulated positions. They all satisfy the same mathematical relationships. This is the core property that makes ring signatures provide both authenticity and anonymity. The verifier gains certainty that someone in the ring signed, which provides authenticity and non-repudiation for the group as a whole. But the verifier gains no information about which specific member signed, preserving the signer's anonymity within the anonymity set defined by the ring. The security proof for ring signatures shows that even a computationally unbounded adversary cannot distinguish which position was the real signer, assuming the hash function behaves as a random oracle. Demonstration function setup. The demo function provides a complete, self-contained example that demonstrates the entire ring signature lifecycle, creating a ring of members, having one member sign a message anonymously, verifying the signature, and testing invalid scenarios to confirm the verification catches tampering. The function begins by printing a header that identifies this as an educational demonstration. This reinforces that the implementation is for learning purposes and helps readers understand they are seeing a complete working example rather than production code. We define a message to sign as a byte string containing the text, ring sign demo. Hello verifiers. Using byte strings rather than regular strings is important because cryptographic operations work on binary data. The message can be anything: a transaction, a document hash, a vote, or any other data that needs to be signed anonymously. The content does not matter for the cryptographic operations. What matters is that we can verify the exact same bytes were signed. The demo creates a ring of n equals 5 members. We use a list comprehension to generate 5 key pairs by calling Keegan 5 times. Each call produces a tuple containing a private key and public key. We then split these tuples into two separate lists: privs containing the private keys and pubs containing the public keys. In a real scenario, each ring member would generate their own key pair and only publish their public key, keeping their private key secret. Here we are generating all keys in one place just for demonstration purposes. We choose signer IDX equals 2, meaning the third member of the ring will be the actual signer. The indices are zero-based, so position 2 corresponds to the third public key in the public keys list. We extract that signer's private key as XS equals private keys at index signer IDX. In a real system, only this one member would know they are the signer and would have access to their own private key, while the other members wouldn't even know a signature was being created. Signature creation and basic verification. The demonstration continues by actually creating a ring signature and performing the basic verification that should succeed. This shows the normal, expected behavior of the ring signature scheme when used correctly. We call ring sign with 4 arguments: the message bytes, the pubs list containing all 5 public keys, the signer IDX value of 2, indicating which member is signing, and XS, which is that member's private key. The function returns SIG, which is a tuple containing E0 in the list of response values. This signature proves that someone among the 5 ring members signed the message, but does not reveal it was the member at index 2. The print statements output information about what was created. We tell the user a signature was created by a hidden member, and we reveal in the output which member actually signed. In a real application, the signing member's index would never be revealed like this. It is only shown here for educational purposes to help readers understand what happened. The signature itself, consisting of E0 and the response list, is also printed so readers can see what this data looks like. For verification, we call ring_verify, passing the original message, the same public keys list, and the signature we just created. This function returns a boolean stored in OK. We then print the result, using a conditional expression to show a green checkmark emoji and valid if OK is true, or a red X emoji and invalid if OK is false. This verification should succeed because we are using the exact same message and public key list that were used during signing, and the signature was properly constructed. This successful verification demonstrates that the ring signature scheme works correctly in the normal case. Someone in the ring signed. The signature was properly formatted, and verification confirms the signature is valid. However, verification tells us nothing about which member signed. From the verifier's perspective, any of the 5 members could have been the signer, each with equal probability. Tamper tests and conclusion. The demonstration concludes with negative tests that verify the signature system correctly rejects invalid signatures. These tests are crucial for confirming that the cryptographic construction actually provides security and authenticity, not just anonymity. The first negative test attempts to verify the signature against a different message. We call ring verify with the bytes tampered message instead of the original message, while keeping the same public keys and signature. The result OK bad should be false because the signature is only valid for the specific message that was signed. During verification, the hash chain will produce different challenges when computed with the tampered message, and the final challenge won't equal E0, causing verification to fail. This test demonstrates that ring signatures provide integrity protection. You cannot take a valid signature for one message and claim it signs a different message. The message is cryptographically bound to the signature through the hash chain construction, where every challenge depends on hashing the message. Any modification to the message, even changing a single bit, will cause verification to fail. The optional third test demonstrates another important property. The signature depends on the exact set and order of public keys. We create pubs_rot by rotating the public key list, moving the first element to the end. Then we attempt verification with this rotated list. The result OK_rot should typically be false because the hash chain was constructed assuming a specific order of public keys, and changing that order changes which public key is used at each position in the verification equations. This test reveals that in this basic ring signature scheme, the order of ring members matters. Some more advanced ring signature schemes provide order independence or use different structures like sorted key lists, but this basic hash chain construction creates a specific circular path through the ring members. Changing the order breaks the chain structure and causes verification to fail. Thank you for your attendance. Please consider subscribing to the channel.